So in this video, I wanted to go over how you determine your rate law for catalytic reactor design. And first of all, I just wanted to point out that on page 685, this is in chapter 10 in this book. So on page 685, there's a table, and it's table 10-4, and it's called Algorithm for Determining Reaction Mechanism and Rate Limiting Step. And I don't know if you can see that, but I recommend looking at that table. And if you have so this book is the Elements of Chemical Reaction Engineering. If you have Essentials of Chemical Reaction Engineering, I'm sure that this table is also in your book, but I'm not sure what page it's on. So anyway, I recommend looking at that table, and I feel like for solving these problems, it's really helpful to just go through the steps, and you're less likely to get confused that way. And also this is really, I mean, if you were comfortable in chapter 3 writing, or if you were comfortable with the material in chapter 3 where you were writing rate laws for different reactions, this should be pretty straightforward, because that's basically all you're doing here is writing rate laws, but you're just doing it a little bit different from how we've done it. Basically, you're adding a step where you're assuming that, or you're saying that one of the steps is rate limiting. So we're looking at so we have absorption, so you have the rate of absorption onto the surface, you have the rate of the reaction, and then you have the rate of desorption. And so I'm setting these equal to each other because one of these is going to be slower than the others, and so the slow one is going to set the overall rate for all these other reactions. So for instance, if your absorption and desorption happen really fast, but your reaction is slow, then it doesn't really matter how fast these two are, because this one will slow down the entire thing. So the effective rate of the reaction is going to be the slow one. So anyway, so I recommend looking at that table, and then I just wanted to go through the steps on that table. So first of all, so this is the algorithm for determining rate law for catalytic reaction. So the first thing you want to do, and actually the first thing on that table, is select a mechanism, and that would be the single site, dual site, or Ely-Radill. And so this is often given in the problem, but if it's not, then, or it might say that it's single site or dual site. So then the single site just means that your reaction occurs on one site on the catalyst, but if it's dual site, it requires two sites, and then the Ely-Radill means that it has a gas associated with it. So, but I'm going to kind of skip over that because I'm trying to keep this to the point of exactly what you need to do to determine your rate law for the catalytic reaction. So I'm going to say the first thing you do is you assume a rate limiting step. And often this will be given too, like it'll say assume that your reaction is rate limiting, or assume that the absorption is rate limiting. If it's not given, then I would say assume that it's reaction limited. And the reason why is because about 75% of reactions are limited by the surface reaction, assuming they're not limited by diffusion. So assume rate limiting step. So number 2 is you find an expression for your expression for your rate expression for your absorption, and the reaction and the desorption. So for instance, if you had, so let's say this is your absorption, you have A plus S to A S. So it's A is S is the empty site on the catalyst, and so A absorbs onto the catalyst. And so if this is what I mean, like if you were feeling pretty comfortable writing rate laws for reactions, this should be pretty straightforward. So this would basically be RAD, so the rate of absorption is equal to Ka, and I'm going to say that's Ka right there, multiplied by PA, the partial pressure of A, CV, which is the concentration of vacant sites, minus CAS, and that's over Ka, where Ka is equal to Ka over K minus A, and this is K minus A right here. So, and using this partial pressure here, that's just convention for how these are normally written. And so that's the only reason that's written that way. You could theoretically write the concentration of A, but traditionally it's written like this. So that's why that's like that. So this would be the absorption. So then you need one for the reaction. And so for that you would have, let's just assume that you have A on the site and is converted into B, but it's still attached to the catalyst. So then this would be, and this would be for a single site, so single site, and so this would be RS, and I'm just going to say S for the reaction, is equal to Ks, so this is Ks, K minus S, and so this is CAS minus CBS over KS. So then the last one would be the desorption. So let's just say that you have this is BS to B plus S. And so then I'm just going to say RDS is equal to KD, and this is KD right here, multiplied by CBS minus PBCB over KD. So then at this point I have hopefully already assumed, I've already assumed a rate limiting step. So let's just say that I'm assuming that the reaction is rate limiting. So then looking at this rate, so this is technically the rate of this reaction, because if this is limiting, then these two can't, even if these two are fast, the entire reaction isn't going to be any faster than this one. And so looking at this, it has a few issues. First of all, we don't have any way to measure CAS and CBS, and so we want to put those in terms of things that can be measured. And this is where things start getting a little bit different from the rate laws we've been writing before, because we want to plug something in for what these are. And we can get that because we know the rates for the absorption and the desorption. And we also know that we can make an assumption that if this one is slow and these two are fast, then this rate constant Ks must be really small compared to Ka and Kd. So we can assume that Ka and Kd are large. And if we do that, then we can make an assumption that Ka over R AD is approximately 0. And we can also say that actually did this wrong. So this would be, we can say that RAD over Ka is approximately 0. And then RDS over KD is approximately 0. And so then when we do that, we can solve for CAS in this equation. So we would have PACV is equal to CAS KA. So then CAS is equal to PACV KA. So then we can plug this into here. And then we have this in terms of the partial pressure of A. And we still have CV in here, and we can't measure CV, but I'm going to show you what you can put in for that in a minute. So then for this one, you have CBS is equal to PB CV over KD. And what we can do with this is just redefine this. So because KD is equal to KD over K minus D. So if we just redefine this and say, I don't know, like maybe KP is equal to 1 over KD, and then we can plug KP in for that. So then we have CBS is equal to PB CV KP. So then we can plug this in for that. And so then you have an equation that's in terms of things you can measure except for the case of CV. So I'll just write real quick what this equation would be. So you have RS is equal to KS, and your rate constant should be known because you determine those from experiments in the lab. And so for CAS we had PA CV KA minus, and then for CBS we had PB CV KP, and this was over KS. So I'm going to erase some stuff real quick, and then I want to show you so we want to manipulate this a little bit because we want to get PA and PB by themselves. So basically we want to pull KA out and write specific, like combine all of our constants into one constant. So basically just simplify this equation a little bit. So anyway, we can pull out Ka. So if we do that, we have Rs is equal to Ks, Ka, and I'm going to pull out Cb too. So then I have Pa minus Pb, and this is still multiplied by Kp, and this is Ka over Ks. And I have the Ka because I pulled Ka out, so I had to divide through the Ka here. And so then I can just say that these are equal to some other constant, and I should have said that that's equal to, well, I already named something Kp, but I'm just going to say this is 1 over K, I'm just going to say K is equal to Kp over Ka Ks. So then I can rewrite this as equal to, so Rs is equal to Ks Ka Cv Pa minus Pb over K. So then this is the end of step 2. So we've assumed a rate limiting step, and then we've written our rate law in terms of in basically assuming that that step was limiting. So the issue with this still is CV, and so step number 3 is to, and I'm just going to erase this real quick. So step number, actually this is step number 4. No, this is step number 3. So step number 3 is to write a site balance, and so we know that the total concentration of sites is equal to the concentration of vacant sites plus the concentration of sites with A plus the concentration of sites with B. And so what we can do is just solve this for CV, and we already know what CAS and CBS are, so I'm going to actually just write that. CT is equal to CV plus CAS, which was P, A, CV, KA, plus CBS, which was PB, CV, K, I think that was KP. So then we can solve this for CV. So we have, well, CT is equal to CV, and this is multiplied by 1 plus PA, KA plus PB, KP. So then CV is equal to CT over 1 plus PA, KA plus PB, KP. So then we can plug this in for that. So if we do that, we have RS is equal to KSKA multiplied by CT, and this is PA minus PB over K, and this is all divided by 1 plus PA, KA plus PB, KP. So this is all in terms of things that we should know or we can measure. We can determine the constants from lab experiments. We can measure the partial pressures. We should know what our total concentration of sites is. And so this is actually skipping to step 4. So step 4 was really to derive the rate law, and so combine steps 1, 2, and 3, and I kind of combined them as I went along. So that's what that is. And then the last step is to compare this with data. So how do you know if this is right? Like, how do you know if the surface reaction really is limiting? And you can determine that because you can compare this rate with with data, so with the rate that's been measured in the lab. And if the rate that you're measuring in the lab doesn't match what you're expecting based on this equation, then you know that the surface reaction wasn't actually rate limiting. And so then you would go back and redo this, assuming maybe that the absorption is rate limiting. And you would re-derive this equation, assuming that, and then compare that to the data. And the steps for this are exactly the same. It doesn't matter if you assume that, it doesn't matter which one you assume is rate limiting, you still go through the same steps. And so this should be pretty straightforward. So I'm just going to erase the board, and then I want to just write down the algorithm real quick, just so it's outlined. And all right, so step number 1, and these are also the steps on that table I showed you at the beginning of this video, so I highly recommend looking at that table. I think it's really helpful. But this is select a mechanism. And this would be single site, dual site, etc. And so a lot of times this is just going to be given, like you're going to know this, but if you don't know this, then you need to select what it is for your reaction and then write your reaction. So step 2 is assume a rate limiting step. And a good choice is to start with surface reaction. So basically, assume that your surface reaction is limiting if you're not told what's limiting. And for step 3, write rate laws or expressions for absorption, your reaction, and desorption. For step 4, write a site balance. So this would be your total concentration is equal to CV plus whatever you have. So for what I just showed you, it was CAS and CBS, but you might have more than that in your particular reaction. So this is just an example. So 5, derive the rate law. So basically combine steps 2, 3, and 4. And for 6, compare with data. So for these problems, if you need to write a rate law for a catalytic reaction, just go through this in an ordered manner, because it's going to be a lot easier than if you're trying to jump around and getting confused. And so just you'll probably start here, because you'll probably be given these 2 things, but just in case you're not, then start wherever you need to. But just start writing down your rate laws, and if you're having trouble writing these down, I highly recommend reviewing chapter 3, especially the information on reversible reactions, because it's basically the same idea, same thing, and the only difference is you're writing for a catalytic reaction instead of the reactions we have been doing.